Yeah, not a problem.
She comes back.
So, all of you are undergraduates, is that the story? All right. Have any of you actually written anything for scientific reasons so far? One. All right. Are you all at CUNY schools or more widely? Okay. So how many of you have more liberal arts background and how many? Okay, so the rest of you are more hard science? That gives me some sense of what I'm working with. Do any of you did any of you growing up not speaking English as your, okay. I guess I can tell you something a little about myself in the meantime to keep things moving along. So I'm John Timmer. The email you should probably contact me at is there. Quick question. So I could either post PDFs that will be useful to you on a web space or have them printed out in advance of the class. Which would you prefer? Print? Okay, so you will have one next week then. So to give you some sense of why I'm here, I did my PhD at Berkeley far too long ago at this point, and spent about between 10 and 15 years doing scientific research, published about 9 papers myself, and then about 5 years ago began a transition to journalism, and I am now primarily a journalist, so I've sort of done both science myself and now focus on writing. Are you the last?
Yeah.
Okay.
Girl, do you know if anybody else is coming or talking to me? I haven't seen anybody. Okay. All right. I think we can start then.
Okay, great. Okay, no problem. I'll keep talking. Don't worry about it. So basically, I now do writing as a career, but I have a strong scientific background. I'm a science journalist. The other thing I do is I teach a scientific writing class at Cornell Medical College, just a few blocks away over on York Avenue. And also I work for their Office of Research and Sponsored Projects on a freelance basis. Anybody where English is not their primary language that is submitting a grant gets to send it in to me, and I go over it and clean up the language for them to make sure that the grant is judged based on its content and not based on misunderstandings between the reviewers and the writer. So I care deeply about getting scientific communication right, and hopefully, by the end of several lectures, you'll be up to the point where you'll be able to do it well. So one of the things that you'll typically experience as you go through the scientific education process, if you go on to a PhD and such, is that you'll be expected to do more and more writing, and ultimately as faculty, your job will consist of largely writing grants and writing papers or editing papers written in your lab. And amazingly enough, everybody just assumes, well, you can write and you could do science, so you must be able to write about science. And nobody ever bothers to tell you that there are easier ways to write about science and ways to do it better. So this is a bit of an attempt to try to get you to the point where you do a better job than you would if you were just expected to go through it on your own. Are we set with the recording yet? Okay, so we're all good. All right, so the last thing I want to say is feel free to interrupt me at any point. If interruptions start taking it out past the point where we're going to finish up in a timely manner, I will cut you off. But for the beginning, ask me questions if I ever say anything that's not clear. So to understand how to write science well, you have to understand what the whole point is. So when we say scientific writing as opposed to just writing, what are the key features of that might differ from some of the writing you've done for college or otherwise? So the main thing is scientific writing, it may seem obvious, is about conveying ideas and information. So you want to make sure that your audience, who may be rushed, who may be skimming an abstract, who may not be paying full attention to you, gets as much information as possible out of that. And so, it's easy to say it's about conveying ideas, but it's remarkably easy to get sidetracked, get bogged down in diversions, go on tangents, and lose the focus on the ideas you want to be conveying. So it's something you need to keep in mind the whole time. The next issue you need to do is fit these ideas into the current body of knowledge. The lone genius who works away with no historical scientific baggage essentially doesn't exist anymore. You're always going to be working in a field where there is prior relevant information. And what you need to do is ensure that whatever you're about to talk about to your reader, or I should say write about, whatever you're about to communicate to your reader fits in with what they likely already know about your topic area. And depending on how narrowly or broadly you define your topic area, that could include science itself down to something very specialized about the immune system. So, a key part of writing about science is to get your reader in a frame of mind where they know why your results, why you're telling your reader your results in the first place, and where they fit into what they probably already know about your field. The last thing is that you're trying to convince your audience. So this may sound like you're sort of selling your science in a way that's inappropriate, but in the end, once you've done the work, if you don't have a clear idea of what the implications of that work is or are, you shouldn't be writing them up. Data without a clear model to fit it into is nothing more than an anecdote, and it doesn't do anybody any good for the most part. So you should have a clear idea of the arguments you're going to be advanced based on your data. There may be more than one that's compatible with your data. It may fit in nicely with what was already expected, but you should know what that is. And in doing so, you want to bring your reader along with you. And if you're not feeling comfortable about trying to convince your reader of your opinion, then again, you should probably be reevaluating whether you're ready to write up your data, whether you need to go back and do more experiments, so on and so forth. So ultimately, all you're trying to do is convey to your reader why your data convinced you of your current thoughts. Does that make sense to everybody? So it's not some sort of unethical attempt to prevent a one-sided view of things, but it is an attempt to sort of bring your reader into your mind and convince them of what's convinced you. The reason all of this is challenging is because your data doesn't speak for yourself. It tells you a limited amount of things, what you saw when you performed a specific experiment. But a reader will need to know why you did the experiment, what testable consequences you are looking for, the very basics of science itself. Science is based on predictions that have testable consequences. You have a model, it should have things you can test, and your data is meant to mediate between the predictions of your model and what you can actually find out about whether it's valid, whether there are exceptions to it, and so on and so forth. So, why do we try to do all this? So if the wider scientific community doesn't recognize what you're trying to say, you might as well not bother saying it. You're not writing for yourself. You're writing because the data you feel you've generated is important enough that other people should know about it. And the classic example of this is Gregor Mendel, who figured out genetics about 50 years before anybody else, didn't write it in a way that the scientific community could appreciate it, and it sat around with nobody paying any attention to it. And that wasn't just a loss for Mendel. We all know who Mendel is now. But it was a loss for the scientific community, because they could have been doing experiments based on what he figured out for decades, literally. Yeah. So it's a waste of time if you have valuable things to say and you either don't bother or say them in a way that nobody else realizes what you're talking about. The other thing, and I sort of touched on this when I mentioned the editing of grants, is that you want your evaluations based on the actual ideas. You don't want people hung up trying to figure out what you're trying to say. You want people to go through, have a clear idea of what you're testing, why you've reached the conclusions you have, or especially when you're writing a grant, you want them to know exactly what experiments you're going to propose and why those experiments will answer key questions in the field. Otherwise, why would anybody give you money? And money makes science go round. The other thing is science is a community-based activity. If you convince a small circle of people in your department or your own grad students and yourself and so on and so forth, you're really not playing a part in the community activity that's science. What you're trying to do is exchange ideas with your fellow scientists and have them evaluate those through either processes, as formal as peer review of a paper or grant, or as informal as sitting over a bar, sitting over a beer at a bar and talking over ideas. So if you can't communicate your ideas, you lose out on other people's perspective, and they can provide an important reality check on your own thinking. They can help make sure that you get informed of data you weren't aware of otherwise. There's lots of ways in which they can really improve your thinking on matters. You haven't missed much. Basically, I'm telling you why you should care about scientific communications, and there's lots of reasons, but the key thing is if nobody understands what you're trying to say, then you might as well go home. So one of the things people have issues with when they're first starting out writing about science is that they have a mistaken idea of what they're trying to do. One of the biggest things that everybody does is just say, well, I'll just tell people what experiments I did, and there you have it. And a historical reconstruction usually isn't that informative to everybody. I mean, why tell them what you did on Wednesday when you came in and ran a gel? What they're interested in are the data and how they fit into a bigger picture. And a historical reconstruction doesn't convey that. How many of you have actually performed research so far? So, okay, great, most of you. So how many of you have gotten results that then cause you to go back and reinterpret experiments you had done earlier? Exactly. So if you give somebody a historical reconstruction when you're attempting to tell them why you did things, you're going to be leading them down dead ends. And although that might be, entertaining to a certain extent, it doesn't advance the ideas you're ultimately going to want to get across. So, you'll actually often have people who are advising you just say, well, write up the results first, and then you can work from there. And I tend to think that's a bad idea, give or take exceptions, because your first thought on writing the results are, well, I'll just tell people what I did, and you get the historic reconstruction. So I would say you need a wider framework that you're fitting the results into before you even know what order to present them in and how to maintain a logical flow through them. So definitely avoid that. The other thing is that people have a strong tendency to think all of my ideas are worth telling you about. And that's natural. If you've got ideas you like, you will want to convey them at one point or another. But a scientific paper isn't the vehicle for doing that. Because in general, you will start heading down short digressions away from the main themes of your paper and then have to jump back into them again. And you're leading your reader off on tangents they may have that may leave them losing track of the bigger picture. And again, you really want to focus on the big picture. So keeping your presentation narrow and focused may not get everything across that you want to, but it will definitely give people a clearer sense of the important things. So the classic example of this is Watson. How many of you have read Watson and Crick's DNA paper? So towards the end, there's a famous phrase where they say, "It has not escaped our attention that this structure has implications for the replication and transcription of DNA," or something along those lines. Basically, it's one sentence, it's not a major tangent, but it tells everybody that they have lots more ideas, and if anybody's reading the paper and thinking the obvious, they're already there. And that's a good way of handling things if you really feel that you need to convey additional information. But, a sentence isn't a big distraction. What you should avoid are whole paragraphs that sort of jump from idea to idea so fast that the reader can't figure out what you're saying. The other thing is it shouldn't be style over substance. What you'll find is as you get better and better with writing, you can get away with a lot more. And it would be very easy to, if your data are consistent with 3 models, to play up one, slide the others off into a side thought, and give a somewhat misleading idea of what your data indicate. So that's something you have to avoid. And I doubt if most of you are undergrads that this will be an issue for your next few years. But as you get older, there are some scientists who are on the borderline of what's ethical in terms of ignoring other people's contributions or ignoring alternate interpretations of their work. And it can be a serious problem, and it's something you should try to avoid. So does all of this make sense so far? Again, I welcome interruptions, so please do. So what are the basics of scientific writing? What I'm going to try to do today and in the next lecture is get you up to speed with what you should be doing when you're writing about science so that you can start working on, I believe the undergraduates have a report due at the end of this that I'm supposed to provide feedback on. So what we're going to try to do is get you up to speed very quickly on science writing. You could start writing out things like the background to your research, and then I will go on vacation to England to see my brother-in-law get married, and when I come back, we'll have a few more lectures on some other things. At the same time, I'll be hopefully receiving some writing samples from you, and then we'll do some one-to-one meetings to sort of go over that and try to make sure we smooth over any rough spots. So what follows today is extremely practical advice on how to do the actual writing in terms of word choice, sentence structure, and so on and so forth. What will happen in the next lecture is to go through and tell you about different forms of writing, so abstracts, full papers, grants, so on and so forth. And then we'll move on from there. So today what you should be paying attention to are the basics of good writing. And the basics, not surprisingly, are the same things you've already learned about for many years. It's word choice, how you structure your sentences, and how you organize paragraphs. What you'll find the difference is with scientific writing, you're structuring them always to create a logical flow between ideas and to always make sure your reader knows where your ideas are going. So if you're writing fiction, a little dramatic tension or surprise ending is a great thing. If you're writing about science, your reader will get lost before they get to the surprise ending. It may seem dull, but you never want to surprise your reader. And so if any of you have written for other purposes, this is something you really have to keep in mind. So the idea is to use words, sentences, and paragraphs to lead your reader through a logical train of thoughts to convey the key ideas. So you never want your reader either guessing where they're going or wondering where what you're saying fits into the larger picture. And that requires an incredible amount of focus. So the main issues with words are primarily being descriptive versus using jargon. So how many of you have read through a paper where you lost track of what a 3-letter acronym stood for about halfway through? Right, so it's, there are obviously very, very good reasons for using 3-letter acronyms because lots of journals have strict limits on the number of words you can use for writing for your paper. And clearly you get a lot of words by shortening things down, abbreviating, so on and so forth. But if you overuse them or don't sort of reinforce what the meaning is partway through, you're losing your reader. So it's a careful balancing act between going overly verbose and just subtly reinforcing what the meaning is. Because there are ways to indicate what a 3-letter acronym is all about just by adding a few extra words next to it here and there, which hopefully we'll see a bit in the example. The next thing is consistency versus repetitiveness. One of the things when you're writing for English purposes you've probably been told is you want to use different words to keep the reader entertained so that they're not constantly thinking they're hearing the same thing over and over again. The problem with that in scientific writing is, yes, it's good to avoid repetitiveness, but if you don't use consistent language, the reader's not going to know that you're referring to the same thing. So if you've had the tendency to use the same term over and over again in consecutive sentences beaten out of you over your past education, you may want to resurrect it when you're writing for scientific purposes. So how do you actually write well based on word choice? One of the biggest things you can do, and one of the things people oddly avoid doing, are using what are called schemas. So schemas are, you can view them as a mental framework that is widely recognized, and people are able to take your ideas and slot them into a pre-existing understanding. What I mean by that is one of the basics of science is that you have models that have testable consequences. But you would be shocked at how few people say, our model is this. A consequence of the model is that. If you do that, people avoid doing that because it sounds kind of trite. But if you do that, everybody knows exactly what you're trying to do there because they all know you've got a conceptual model. It has something there are ways to approach it experimentally. And very few people do that. Another thing that came up recently is people did a word search on papers about antibiotic resistance in medical journals, and you would be amazed at how few people use the technical terms for evolution. Now, if I say evolution to you, you immediately get selective pressure, changes in gene frequency, population dynamics. It brings in a lot of concepts for free just by using the appropriate terminology. So that saves you words in the long run. It helps your reader understand what's going on. And why not use evolution if what you're talking about is the evolution of antibiotic resistance? So that's something you really, people ignore the obvious terms because, oh, it's obvious. But what's obvious to you may not be obvious to your reader, and you really, you get so much of a rich understanding for free just by using things people already recognize. And schemas is just the technical term for that. The other thing, so again, please interrupt. I feel like I'm hammering you over the head incessantly here. Expand text for explanations. This gets into the jargon versus overuse of words. Definitely the first time you introduce a concept, You need to spend the text to make sure the reader knows what the concept is. And it's very easy if you're in a field like immunology to assume, oh, immunologists are only reading this paper. But if you write only for a narrow audience, you're, one, not communicating with the full scientific community, and two, you're missing out on the possibility that somebody else will read the paper, somebody outside your field will read the paper, know what's going on, and have ideas. You could find collaborators who know about techniques from, say, a microscopy perspective that can answer a question you've been trying to do with molecular biology. Things like that. So the more readers you can draw into what you're writing about by avoiding overly technical language, the better for you and the better for the community as a whole. So spend the text to make sure you bring as many readers into your ideas as possible. So to give you something concrete, how many of you have a math background? Know what a Markov behavior is? M-A-R-K-O-V? Anyone? Okay. I don't have a math background. I'm shocked I knew this one. So I received papers to edit where somebody said, we used a Markov model to explore this system. What you're doing by that is cutting off a huge chunk of your audience, sending them to Wikipedia, sending them out of your paper somewhere else, or just saying, oh, this doesn't apply to anything I'd be interested in. So a Markov model is something where it's a mathematical construct where the next state of a system depends only on the state immediately. So it's not, you don't sort of use several states back to calculate the next one. It's just this or this is used to calculate the next. Does that make sense? So hopefully you'll understand how I fix this now. So to explore this system, we used a Markov model in which the current state of the system depends only on its previous state. It's not a brilliant explanation, but now the next time, as somebody's reading through this paper, if you're doing mathematical modeling of a biological system, ultimately you want biologists to validate your ideas. And if you use jargon without them knowing what you're talking about, they're lost. I've had, how many of you know what an independent variable versus a dependent variable is? Okay, that's good. Yeah, you would be surprised. I had to use zero math for about 15 years, and I had forgotten it, and I had a huge argument with somebody. This is the basics of science. Everybody should know this, but I see at least 10 of you, in addition to me, had no idea what it was by the time it came up in a paper. It doesn't take much text to explain the difference between an independent and a dependent variable. And if you do it in your paper, you're bringing in readers who would otherwise say, not interesting, and move along. This is something I was talking about. Frequently arises, develops. That is what MDs are using to describe the evolution of antibiotic resistance. Now, if you say develops to me, I have a background in developmental biology, and you're using the wrong schema there, because that to me says morphogen gradients, intracellular signaling, various things relevant to developmental biology. And when you're talking about evolution and using develops, you're just confusing matters. So again, this thing's really easy to fix. The hospital environment provides selective pressures for the evolution of antibiotic resistance. You're using two technical words, tells people exactly what you're talking about in the right terminology. You're not crossing borders between different fields of research and confusing matters. Next up, not surprisingly, moving up the food chain, are sentences. So sentences are sort of the basic unit of thought. Really, when you're writing a sentence, you should be conveying a single thought, at most two, and you probably need a semicolon or colon between them if you are using two. You really don't want to try to overburden a sentence. The reason for that is, how many of you, when reading a paper, come across something where you get confused, forget what's going on, and have to back up? I don't believe the ones who say you don't. Your first response should be to go back to the start of the sentence you're stuck on. And so if you have this enormous overburdened sentence and people have to go back half a paragraph to get back to the start, you're causing them to do much more work than they need to, and you're making it much harder to read what they're saying. It'll sound a little choppy when you're writing it, but keep the sentences short, keep them focused, keep them zeroed in on a single concept. Otherwise, if you try to put too much, it'll make it hard to follow, and you'll force your reader to go through it several times before they get the point, and you've just wasted people's time. The other trick is to maintain a logical flow between thoughts. So consecutive sentences, you don't want a large logical jump between them. You want your reader to not be reading your paper and suddenly say, what? That doesn't follow, because you're sort of pulling them out of the idea flow. There are easy ways to connect sentences to each other and in a way that maintains the scientific logic of what you're describing. And you need to do that. The easiest way to make sentences easier on your readers, keep the subject and verb close together. It gets very tempting when the subject is something you want to say several things about to start tacking in clauses after the subject that tells the reader more and more about the DNA you're working with, the gene you're looking at, so on and so forth. And the more clauses you put in, the easier it is for your reader to forget what the sentence is all about by the time you get to the verb. And that's a bad idea. If you start with DNA and you're down to enhancer elements somewhere in a gigabase of DNA, they've forgotten where the DNA came from by the time you're using the verb to describe what you're doing with it or anything like that. To keep the logical flow between sentences is that the key thing to do is the first part of a sentence should be connected to the last bit of the previous sentence. So again, if you're talking about a gene and you go through its enhancer structure in one sentence, you need to start with the next one with something about the enhancers, the structure of the enhancers around it. Otherwise, again, you're just popping the reader out. They're wondering why you're telling them what you are because there's no connection between the thoughts. So again, I've got a few examples I wrote up quickly. If you see the DNA is the subject here, was genotyped is the verb part of the sentence, and in between you've got extraneous information about the DNA. And by the time they get to the was genotyped, your readers are wondering about who these 237 subjects are rather than the DNA you're supposed to be focusing on. So it's really easy to restructure something like that so that the two thoughts fall out separately. So DNA was obtained from these subjects and genotyped. You can make that two sentences. It could be even better. End at protocol, start the next one with it was. So to describe how to link two consecutive sentences, so you're working with the end of this first sentence is genotyped. And then the next sentence starts with experimental and control populations. And you've already shifted from talking about genotypes to talking about populations in your study. And they're not connected. So these things are really easy to fix. Basically, you end with genotypes, you start with genotypes in the next one. And that gets your reader, that keeps your reader within the logical flow of your ideas. And again, don't be worried about overusing genotype, because genotype is a schema that any geneticist and hopefully most biologists have a clear idea of what you're talking about when you're genotyping things. So yes, the word keeps showing up in consecutive sentences, but that's a good thing. Everybody good so far? All right, so last step up the food chain before you get to organizing entire sections of a paper or something are paragraphs. And paragraphs really are the key unit. If each sentence should convey one thought, each paragraph should contain a series of related thoughts connected by a common argument. So one of the jokes about scientific communication is that what you do is and this goes for speaking as well as writing, you tell your reader what you're going to tell them, then you tell them what you just told them. And basically the idea there is you want to introduce your reader to the topic that's going to be covered in the paragraph in the first sentence so they know why everything's coming at them. Oh, I should probably have advanced to grouping related thoughts by now. They need to know why the information you're conveying in the paragraph is coming at them. Then they get the information, and then you tell them what the conclusion you've reached based on that information. It's a very, it seems like you're throwing around sentences that'll blow up your word count very casually there, but it doesn't take a lot of extra words because typically you're going to convey those thoughts in the sentences as well. So if you drop them if you drop the conclusions you're reaching out of the sentences in the middle of the paragraph and put them at the end, it doesn't cost you a lot of words. So the key thing is it should provide a structure for the argument. So everything in that paragraph should be related to the point you're introduced. When I say argument, I'm using it in terms of conveying a thought, not in I am really upset with you, just to be clear. Now I've lost my train of thought. See, that's why diversions are bad. Basically, you want to make sure everything in a single paragraph is related to the point you've introduced at the beginning. And one of the things you should do when editing your own writing is look to make sure that's the case. And if a sentence doesn't belong there, you just pull it out. You may look elsewhere in your document to see if it fits in somewhere else. But if a sentence just doesn't hang with the material it's around, it's jarring to the reader, it doesn't help you convey any information. And if it really doesn't fit anywhere else in your paper, you should be seriously thinking about whether it belongs there at all. Because if it's that far out of the general stream of your thoughts, then it's probably an extraneous bit of information. The last thing, which I've already told you, is you need an introduction and conclusion. It seems silly. Introductions are, their own standalone section of a paper, but you really need to tell the reader why it's going, where things are going. Yes.
Along with the separate paragraphs, you need introduction and conclusion within that paragraph.
Yes. So each paragraph, within reason. How much writing have you done? Sorry, I did. Okay. So, you'll see situations where you don't have to have an entire sentence dedicated to concluding or something like that. You could just tack on a clause at the end of the last sentence. But really, you need to let your reader know with an introduction why you're hitting them with all this information, and with a conclusion where, what the sum of that information is. So you can get it, well, my example actually shows you can get away with it to a certain extent. So this is a sentence out of one of my own papers in which I've deleted the introductory, this is a paragraph in which I've deleted the introductory section. And if you'll see, it just starts diving into genes. And unless you really know this system well, you will have no idea what these genes are, why you're looking at them, or why they might be relevant to the larger part of the paper. And all you need to do to fix that is one sentence. So you were looking at the division of the dorsal. So again, this is highly technical, but hopefully by this point you've already read my introduction and abstract and known why I'm talking about the dorsal neural tube and BHLH genes. But the introductory sentence tells you that the information in this paragraph will relate to how the neural tube, so that's the embryonic version of your spine, is divided into distinct domains of gene expression. And then all of this talk about gene expression should at least fit within that framework as the reader's reading it. And then when you finally get to the bottom, you're at the point where you're reaching conclusions based on that information. So hopefully, I don't expect you to come out of reading this knowing, why I was doing these experiments or anything, but you should come out of it knowing, again, just delete the first and last sentences and try to figure out what I was saying there. There's no reason to expect that you should. Whereas just by adding on a couple of reasonably short sentences, you've structured all the information in the paragraph so that it makes a single point about the division of the dorsal neural tube. All the information within that is relevant to how that may change in response to our experiments. And then at the end, what that tells you about the larger picture. And that sort of structure should be repeated at every level above this. So that should describe how you write your introduction, how you write your abstract, how you write your individual sections of your results, where you let the reader know what you're going to say, you go through it and elaborate on it, and then you tell them why that information leads to a distinct and limited set of conclusions. Any questions? So I should say I was counting on people to interrupt me sooner than this. So I am pretty much done.